Okay, so let's continue about that the talk. And this is a second category, is that how does plasma really enhance the flame stabilization, particularly for application in gas turbines. And France made a lot of this kind of test, particularly at Ecocentral Paris. You can see that they say that by using this is at the electrode, and this is at the burner, we can form a plasma discharge between the electrode and the burner. Is like a bluff body stabilization behind that a bluff body. So what it says is that the lean limit is reduced by 10%. That means I can burn leaner. With the plasma energy is about 75 watt. And then we try to say that using a two-stage swirling injector for propane, for example. This is a swirling is the first stage, and they have swirling and the second stage. And the propane and the 1 watt mass pressure with 52 kilowatt. And the plasma basically reduced at the lean burn limit from 0.4 to 0.11. It dramatically extends the lean stabilization limit with plasma power of about 300 watt. And then the aerodynamic injectors, this again, they show that the plasma basically extends the lean burn limit. So you can see that all this kind of experiment from engine and from RCM and from flame stabilization, they all give the magic conclusion that plasma can make it burn leaner, and plasma can be very effective, right? So these are all the things. But remember that you don't know really this is really the kinetic effect. It was questioned by probably one of the students during the time, or due to that thermal effect. You really don't know. All these things until probably middle of 2000 is all talking about the demonstration about the plasma effect in terms of flame stabilization and ignition. A similar experiment done is same university at Ecocentral Paris, basically saying I have a bluff body, I have the electrode, I have formed a discharge behind the bluff body, and see how does the flame regime change. This is Crystal Laws at 2007. Basically saying that by increasing the flow rate or decreasing the equivalence ratio, if you increase the flow rate, the flame becomes longer, and then longer. And if you further increase the flow rate, you form a flame only at the burn exit. So I have three different flame regimes. One is attached, the other one is a longer one, a separate flame regime, the other one is short. So basically what they say that you can say without plasma is the red line, and with plasma is the black line, is the equivalence ratio as a function of airflow rate, particularly at the lower airflow rate, that plasma can dramatically enhance the lean burn limit from probably 0.7 all the way to 0.6 in terms of flame stabilization. So they all show the same thing, but it's very difficult to tell what is the mechanism. And this is that the last slide tried to show you in reforming. And in Tokyo, in Japan, and also in Europe, and people try to using that plasma to reform the methane and CO2 into syngas. So let's say that 400 Kelvin, and the initial methane is here, and with catalyst, you can see that the methane decrease and the hydrogen rise. But with a combination of plasma and catalyst, you can see the hydrogen rise very quickly, and then the methane decrease. So you can see there's also some magic effect of a plasma-assisted reforming. So what we can conclude that the plasma can do a lot of magics in combustion enhancement. The question is that does it really have any kind of chemistry effect, or is it just a thermal effect? And the question is that how do plasma can kinetically enhance ignition, the flame speed, and minimum ignition energy? And what are the reaction pathways if it does a kinetic enhancement? So these are the questions that would not be clearly answered in the previous application type of plasma-assisted combustion. So the next thing I try to spend probably an hour to talking about what is the basics about ignition and the flame speed. You probably take the lecture from Professor Matalon. And I will integrate based on that and try to extend that theory a little bit forward in considering particularly that the heat losses and the stretch, and then show you how that the the chemistry and the transport affect the Lindbergh limit. So the effect of a plasma on ignition, flame propagation, and the burning limit, and the minimum ignition energy. We try to, from a theoretical point of view, what is really governing the process of ignition and then flame propagation and the minimum ignition energy. And then we'll try to see from a chemistry and thermal point of view, and then how does that effect of plasma on them. So first we talk about ignition, then we talk about flame propagation affected by stretch and heat losses. And we talk about ignition and quenching distance and flammable limits. And the question I asked, what is the difference between the critical radius and what is between the critical radius and then the quenching distance in, and what is really governing the minimum ignition energy in theory? How does the electrical field affect the flame propagation? So I'll speak slowly, and I hope you can follow me. So with the help of Professor Martelon, you probably understand one thing is that ignition and ignition limit. For any kind of a mixture, if we have pressure and temperature and concentration, you can write down a governing equation that is that the temperature gradient is equal to the heat release rate, and then the concentration of fuel is governed by this Arrhenius law, initial condition of temperature, initial condition of mass fraction. You can add this equation together and cancel this reaction term, and you get that the temperature correlation with the mass fraction is coupled by the adiabatic flame temperature. This is that you erase one equation, and then you reduce the problem to one equation. You can normalize it by a normalized temperature, normalize heat release rate, normalize activation energy beta, and then normalize the time, and expand that Arrhenius law to a perturbation term of temperature -1 is the adiabatic temperature with activation energy. Then you try to introduce the concept of asymptotic analysis. What is the key point of asymptotic analysis in terms of ignition and flames? What is the key assumption of asymptotic? The theoretical derivation of ignition and flame speed is basically assume that the heat losses and then the radical quenching, they only perturb your temperature by an epsilon order. The epsilon means very small, okay? So you can substitute the equation by introducing a small perturbation. You find the first order, leading order solution, which normally is very simple, okay? And then you put the solution back to the equation, ignore the leading order, only solve the perturbation order, you can get an analytical solution, right? So I think that for ignition problem, it's pretty easy. So when you substitute this one into it, and then you reduce that equation into, this is that the theta is the temperature, and this is the beta is that the activation energy, and this is the solution, this is the initial temperature. So this equation, you have analytical solution. Professor Martelon probably told you that you can immediately find that if the theta -1 is equal to beta, beta is activation energy, which is very big, how big it is. My advisor told me 8, 10, 20 should be fine. So that's what you just assume that theta is close to 1, but it's a inverse of beta order or epsilon order. So you substitute this guy into this equation, and you drop the 1 order, and immediately you get this kind of a governing equation. This is the perturbation, you see. Theta -1 equal to a constant times the inverse of beta. So beta is very large. That means that the theta is order one magnitude, is equivalent to 1. So you can solve this equation, you get this ignition delay. Professor Martelon probably told you. And this is the ignition delay time is proportional to rate coefficient B. the heat release rate, activation energy, and the temperature. And from this equation, you can guess what the plasma can do. As you said, the plasma can accelerate the reaction rate, because the reaction rate depends on concentration, particularly initial radical concentration, very important. So the plasma can generate initial radicals to increase the reaction rate, B, and then to reduce the activation energy, maybe form a new reaction pathway that bypass the reaction of H plus O2 reaction. They reduce the activation energy, and same time can generate a thermal effect to accelerate it. So this is very easy. But plasma can generate a thermal effect. You get the same governing equation. You can introduce a thermal effect. This H can be heat loss, can be heat gain due to plasma. You can introduce that same perturbation that is giving you this equation. This equation can be analytically solved with the expansion, or can be numerically solved easily. Give you ignition if the heat addition, if the heat loss, ignition delay will be changed. So therefore, the plasma really can give you a lot of things in terms of affecting ignition by changing the reaction rate, activation energy, and then temperature. Now I try to show you from a plasma chemistry point of view what it changed the reaction pathway. For example, focusing on two things, radical production and then heating. There are two heatings, slow heating and faster heating. Okay? So from radical protection point of view, if you have a plasma energy really low, what do? The electron collide with oxygen, it generates vibrational excitation, probably oxygen. Or the electron, at 1 electron volt, electron heats oxygen, generates O2 singular delta, is electronic excited. If you further increase that electron energy, you can directly dissociate this one to form two radicals. And then if your electron energy is even higher, you can break down the oxygen into ions and electrons to magnify the plasma effect. So these are the radical production process, electronic vibrational excitation process that could change your reaction pathway. For example, H plus O2 reaction, which is very important in combustion, but H plus O2 singlet, the energy barrier is much, much smaller. It dramatically increases your chain branching reaction rate. Second, electron-ion recombination can generate heating, recombination. These are generate a attachment. This is energy transfer. They give you heat to accelerate the combustion process. And then the third, the energy transfer due to the electronic excited species. For example, nitrogen is electronically excited to ABC states. That excited nitrogen collided with oxygen, they break down radicals. So at the same time, the O&D is that the electronically excited atomic oxygen, they can not only generate H abstraction, but also they can break down the CH bond, bring itself between them. It's called oxygen insertion effect. It generates a new reaction pathway that can affect your reaction pathway. This I just said, that H plus O2 reaction was much faster. And it generated this a vibrational energy to generate radicals, and all this energy transfer process. So this basically generates slow heating and also generate radicals. So the plasma has many ways to generate new reaction. You don't see it in combustion. It can have ways that generate heat that can be fast, it can be slow, depending on the process. So this how that generated affect the combustion kinetically. Then we have to see which reaction really play a big deal. That depends on the electrical field strength. As I said, different electrical field strengths, they have different reaction channels. And then, for example, a simple calculation, a hydrogen ignition. Hydrogen ignition, chain initiation is governed by these two reactions normally. The first reaction probably is slightly faster than this one, but this reaction is really, really slow. Hydrogen itself reaction is very fast, but this initiation reaction fast. Let's say that if we have ignition delay time, if this is that the more fraction of radicals is generated by plasma. Let's say that you generate a hydrogen atom, OH atom, and O. You can see that if we're adding OH production by plasma, you reduce that the a 1 order of magnitude of ignition delay. And then if you generate O atoms, you further decrease. So producing O atoms is more effective than producing OH radicals and in a hydrogen ignition process. Okay? Why? So this is very easy to understand. If you produce an OH reaction with hydrogen generates H radical. Okay? If you produce an O atom, the O atom produces and generates 2 radicals. This is why that produce atomic oxygen is much more effective to produce OH, because this reaction is faster than this reaction. So they can generate 2 radicals, so they're accelerated. So this is basically showing that because that the ignition process is hungry for radicals. Any kind of process, if you can generate radicals, and then you can potentially reduce the ignition delay time just because accelerating the chain initiation reaction. Okay? This is one thing. So if you're looking at that a gliding arc, as I said, we can create a gliding arc and stabilize by a magnetic rotation, and we put a fuel from the top and air from the bottom. Plasma can potentially generate NO. Everybody knows that NO has a catalytic effect. Catalytic effect of what? Of converting H2O2, which is less active at a low temperature, to OH, right? So let's see how that does. So this is at the ignition temperature. This is at a different strain rate in a countable flame for a hydrogen. You can see if you heat it, you need a 950 Kelvin to ignite it. If you're using plasma, they can generate NOx, for example. They can potentially reduce that ignition temperature by about 100 degrees, because this is the termination reaction of H radicals, and this is the plasma generation of NO. They convert this H2O2 to OH, and this come back. You add these 2 equations together, that means that 1 H2O2 go to OH. This by plasma. It's very clear. This is not something new. It's been found in the 1980s. But just try to show you that plasma can actively produce NOx if you're using high temperature arc. Question?
How long does a species last after they leave the plasma environment?
How long? But NO is a very long time. So even you live for a very long time, NO is still stable. Some radicals, they will die depending on the temperature. But NO will be there. The singlet oxygen potentially can be there 300 seconds to be alive. Okay. So this is that the ignition diagram. Everybody knows that this explosion limit, which is the pressure for hydrogen. This is the temperature. You have a pressure limit. You have a second explosion limit. You have this one. I don't want to repeat it. I think that the other professors will tell you what it is. So on the left-hand side of this curve, you cannot ignite it by itself, right? But if with a plasma, there's no explosion limit at all. You can always ignite it because that's the chain branching process. This limit is basically a competition of chain branching and termination. But once you have plasma, you generate a new reaction pathway so that it can break down the explosion limit. So, and then if you're looking for a little bit more complicated, I think that is for hydrogen and methane. For methane, these are the chain initiation reactions. They are quite slow. And then you have a chain propagation and the branching reactions. The most important thing that you can generate a methyl. The methyl plus O2 reaction, they generate for a methoxy and atom, and generate formaldehyde for OH. These reactions is very, very slow in methane reaction system. That makes a methane ignition particularly difficult, right? And then this another reaction at high pressure, you form a lot of H2O2, and the methyl plus H2O2 reaction is becoming important at low temperature and high pressure. But you don't have a lot of a H2O2 formed, and until you go to very high pressure process. So these are the 3 reactions, the limiting that the ignition process of methane. If there's any way that you can accelerate this reaction through plasma, and you can potentially accelerate a methane ignition process, in addition to the chain initiation process. So this is that a modeling by Starikowskaya and published in 2008. This is basically auto-ignition at 1530 Kelvin above the methane oxygen. You can see that is auto-ignition. You can generate some kind of a intermediate species and radicals here and the ignition process. But if you have a plasma-assisted ignition, in the beginning you drive a lot of radicals. These radicals, they decay due to radical recombination, right? But during the recombination process, they partially oxidize the fuel. They form CO2 and form water and form formaldehyde. They oxidize the fuel. They generate additional heat. This additional heat drives the ignition and makes the ignition delay an order of magnitude shorter due to that the combined effect of radical production and thermal heat extraction from the fuel, right? This is a very simple calculation process. And the next thing you try to see, if you run a shock tube, you generate a homogeneous plasma discharge, and you see how much ignition delay time is shortened in the process. So this is done in Russia by also Starikowskaya. I can say ignition delay time, this is at the temperature, and this is methane, is auto-ignition. Ignition delay is very long, 100 probably 100 microsecond. So, but with a plasma discharge, you can see that there is a methane, plasma-assisted ignition, the similar pressure range reduced by 2 order of magnitude decrease. So this is that the dramatically enhancement effect by ignition process mostly due to the radical production process. It's this temperature at the 1500 Kelvin, and you don't really need. So you can see that it's a very high temperature process, and then the radical production is really effective from plasma-assisted combustion, particularly for scrambled engine. And this is that experiment we did that for methane ignition at the same time. That you can see that by using a gliding arc, magnetic gliding arc, the auto-ignition temperature can reduce by 200 Kelvin. And due to that, the NOx and production process. So that means that the plasma does have kinetic effect. But the kinetic effect is mostly limited to ignition process, right? Either through catalytic conversion of HO2 to OH or through their initial radical production process, right? This is the simple experiment. So this is the experiment I just showed you before. Combustion, you have this ignition extinction S curve, and by using plasma, you can change this one to accelerate ignition to ignition so fast there's no extinction anymore. This again is that acceleration of ignition by radical production that has a chemistry effect, not thermal effect. Okay? So from this kind of fundamental research, we become more and more clear that the plasma, not only just because it has a thermal effect, it does produce kinetic effect through simple reason, radical production, NOx production. But this is not very interesting because we know that radical production can generate accelerated ignition. We know that NO has catalytic effect, but plasma can do something more beyond that? So that is the question we want to ask, and when we moving forward for the research. So let's see that most of the transportation fuel, and you have two-stage ignition. For example, a gasoline and a jet fuel, you have low temperature ignition, you have high temperature ignition. For example, this is an heptane. If I plot that the temperature as a function of time, you initially have 650, and then first stage ignition is low temperature, and then high temperature ignition here. You have two-stage ignition, and sometimes you may have three-stage ignition depending on the temperature. Now, what the role of plasma can do, at what condition plasma really can accelerate combustion process kinetically, not thermally. So the first thing you have to ask yourself, if you're using a plasma, how much radicals are you producing in plasma? How much? For high temperature plasma jet, arc, yes, you can produce a lot in a small volume, right? But for non-equilibrium plasma, we call it weakly ionized plasma, and the radical production is really, really small. We hope that the small radical production will have a potential impact of combustion. If you need a large radical production, then you just heat it thermally, right? So let's say I have a plasma. That plasma can generate some magic. That it can generate the radicals I want it. It can generate the electronic excited oxygen, electronic excited nitrogen. But remember, this radical production has to be very small because that non-thermal plasma. And then what is the hot ignition? For hydrogen ignition, everybody knows that these two reactions govern everything about the Chern-Branchen process. Chern-Branchen and then process. And this reaction rate at 1200 Kelvin is much faster than anything of radical production of this process. So from kinetic theory, you say that if something, use this one at this temperature, high temperature ignition temperature, they're already faster than this. Do you care that the plasma gives you some radicals? You don't, right? Particularly for flames. What is the temperature the flames start to extinguish? About 1500 Kelvin, right? About 1500 Kelvin, the flame will die. At 1500 Kelvin, this reaction rate is even faster. So does the plasma generate radicals help anything about that flame extinction? Not. They only help to contribute adding more heat to accelerate this temperature-dependent reaction rate, right? So in conclusion, what I want to say is that non-equilibrium plasma, it does not help much about flame propagation and extinction because at flame propagation and extinction temperature, the Chern-Branchen reaction rate produces radicals much faster than the plasma itself. The plasma only plays a role of heat addition, okay, to accelerate this Chern-Branchen reaction because they are temperature dependent. What if you look at the intermediate temperature? At the intermediate temperature, the fuel becomes formaldehyde ethylene at this stage, and then attacked by radicals form HCl. The HCl reaction with O2, they form a low temperature form HO2 and peroxide, and this peroxide dissociation to two OH radicals. This governing that the transition from low temperature to high temperature ignition. This is very temperature sensitive and is very slow compared to this one. So then you look at this diagram, you say, aha, I have an opportunity. What is the opportunity? My plasma can enhance my transition from low temperature to high temperature because my rate here is much faster than this guy. So if you want to design a plasma to control combustion, the first thing you think about is they have to be more effective to control that intermediate temperature ignition, the transition from low temperature to high temperature, right? What if at this stage, that the reaction rate is governed by RO2 isomerization to QOH, and Professor Bill Green will tell you what is that the rate constant to estimate. And this reaction will generate 3 radicals in the process. And this reaction rate is even slower than this. And then what do you see of plasma? The plasma can see that the plasma can potentially accelerate this, can more potentially to accelerate this. So you really want using plasma to control that the ignition transition, control low temperature, is much more effective to control here. Here is really that when the flame is going to die and you fire a plasma to stabilize it through mostly thermal effect, a little bit kinetic effect. But here, most kinetic effect. When I look at this diagram, I draw this diagram when I try to, probably about 2014, and I thought that I probably can use plasma to generate a cool flame. And I asked my research staff, he wanted to do it. He waited for probably half a year, does not want to do it. At the lunch table, I told him, you got to do it this afternoon. I wait for your call, and then you tell me whether it works or doesn't work. And then at 3 o'clock, he called me and said, Professor Chu, I saw a cool flame there by doing a plasma. So this is the first thing we say that the theory is not theory, that this rate rate ratio basically tell you what can be done, what cannot be done. And the more kinetic effect for plasma-assisted combustion at low temperature. This you can see. This is that the S curve again. This is that production of formaldehyde in DME flame. Ignition, low temperature ignition, high temperature ignition, and then flames. By working on plasma, you can see it dramatically accelerates low temperature combustion, and the process becomes like that. You can see that the low temperature ignition, you dramatically accelerate. Accelerate even become faster than the high temperature flame. You don't have this kind of S curve anymore. And then this kinetic pathway, I don't want to say anything about it. So this is that another experiment is a flow reactor. It's conducted by Professor Rich Yetter in Penn State. He has a quartz reactor and put two electrode outside the quartz reactor. Is that with a nanosecond dBd discharge. And the whole thing is put in the oven and is heated. He wants to make a discharge upstream and see how that a species change. And this is that the curve. What did you see? See, this is probably a species of as a function of, I guess, is the temperature. You can see that just with that the heat. I think probably that's just using a thermal autoignition. You are here. This is the temperature. Threshold is about 1100 Kelvin. But the same fuel, alkanes, if you're using plasma, you can see that the ignition happening even at 600 Kelvin. Some of the fuel is already oxidized. What does it say? It says the same thing what I said. It is that plasma dramatically enhance low temperature oxidation of large alkanes, because that they produce radicals much faster than the low temperature chemistry can do. If engine ignition is limited by that the ignition process, particularly in HCCI or in some kind of a partially premixed compression ignition engine, plasma has the opportunity to do that, to control ignition. This is at a Gunderson at the Southern California. They're using this coronary discharge. And then they are basically saying that they shorten the ignition delay time. What they say that this might be that the process. But they really don't know. They just guess it. There's no fundamental experiment to show that these two reactions are relevant or important. Maybe they are. But this experiment, the global type of experiment of ignition delay, you can't tell anything. You have to do a shock tube experiment in some kind of time-dependent measurement in order to understand what is going on, right? So time-dependent measurement in plasma is very important to understand what is the kinetics. So, and the next thing I try to say, we understand what is the ignition. It's computation of radical production. So the next thing we try to do is that what is that flame propagation? And again, this is a flame propagation is that the conduction or the ignition process. You can write down the two equations, energy and fuel. You add these two equations together, you eliminate one equation, and you only need to work on one equation. Okay, that's what I normally do. So you integrate from upstream to all the way downstream. You can find that the adiabatic flame temperature. And then you can integrate from any place in the front and to the end of the reaction zone. You can find another equation between temperature and concentration. So this is basically that the correlation between temperature and the reaction. So how do I find the flame speed? In order to find the flame speed, you need a jump condition across the flame, right? That Professor Martin will tell you. The jump condition basically governing that the enthalpy conservation. And then the reaction diffusion system. So I try to show you that normalize it, you generate using activation energy better, and introduce that a new parameter that normalizes the fuel mass fraction. So what do you do? That this is the reaction diffusion system, because that the fundamental assumption in combustion is that the reaction is governed by a reaction diffusion system. In the reaction zone, you can ignore the convection term. So you can write down that the reaction diffusion system You can integrate this, rewrite this equation. You can integrate it, and integrate it from the flame front, negative flame front to the x. You can find that this is that the jump conditions, the concentration gradient at that before the flame front. After the flame front, of course, all the fuel is consumed. Is gradient is 0. The fuel concentration before the flame front is this. This is that the jump condition you derived from the governing equation. And then you can integrate that equation, and from the next infinity to the front, and you get that the flame speed is that proportional to the Lewis number, and molecular weight, reaction rate, and activation energy, and activation. So this is that the mass burning rate. You can find it on all textbooks, and different people divide different way. I like a activation energy analysis because they're very rigorous and give you an answer. But you can see that plasma can do what plasma can do is the same as the ignition. You can change that reaction, activation energy, temperature, and also that the reaction rate. But the question is that the plasma is more like not only is not adiabatic, they can introduce additional heat. How, and also that they can break down the large fuel to small ones. The question is how does this transport process and how does that heat addition affect my burning limit, right? Everybody knows that the flames has a flammable limit, and what does the flammable limit is governed by what? You probably have, I'll show you something. In the next 30 minutes, you will feel very interested in about what is the flammable limits. And then we start from the governing equations, and then we can reduce the equation by normalization. Here I introduce that the heat losses term, H, to mostly the heat loss is due to radiation or heat conduction. It doesn't matter. And then you can find that the analytic solution upstream and downstream, because there's no reaction, it's only convection diffusion system. Then you need a jump condition across the reaction zone and get the solution. And then this is the same thing. I don't repeat it. You get perturbed fuel concentration and the temperature. And everything you have to integrate from negative infinity upstream to the flame front. And you get the jump condition of that the perturbation. And then what do you get? You get that this is that the mass burning rate, log equal to 2H. H is normalized heat release, right? Every extinction phenomena is governed by this reaction. If you plot this equation, if you get this equation, you get very excited, because for me, I get very excited because I know this one governs the extinction limits. So we will plot this equation as a function of heat loss. Remember, the heat loss is normalized by the radiation heat loss, normalized by the flame speed. As you increase the heat loss, the flame speed decreases at a certain point, extinguish. When the flame speed reaches to 0.61, which is the inverse of a square of E, and the flame will die. Beyond that, the flame cannot propagate. Flame does not propagate because you have a large H. This H equal to inverse of E. What do you mean by large H? The large H means that either has too much radiation heat loss, or you have too small of adiabatic flame speed. That means that you have too lean of the mixture, right? The lean of the mixture will causing a large H. The more heat loss will also cause a large. So this extinction limit governs two things. Govern the limit of heat loss quenching the flame. Govern the limit of flammable limits if that the fuel is too lean to burn. And how does the plasma can change it? Well, the plasma can change it, or a lot of things that can change it. It can not heat loss anymore. It is heat addition, right? It can extend the limit limit by adding heat. And also that by enhance the change that the beta and reduce the beta activation energy, make this normalized heat loss small. So from theory that plasma can do this kind of things. So this is at the quenching diameter, and Professor Matalon has a paper, and you can talk to him. But
a few slides ago, you mentioned that the most efficient effect of the plasma is in the low temperature chemistry.
yes,
But this is all high temperature effects.
this is the high temperature effect, but this can also apply to low temperature too, if you assume that low temperature activation energy is high. This kind of asymptotic does not limit you to high temperature, low temperature. The only thing you need to assume that beta is large. The beta means is activation energy. If the low temperature chemistry activation energy is large, this also apply. Okay. So this is at the quenching diameter. If you have a channel and you flame propagating inside, and then you have heat loss to the wall, and then to a certain, if you reduce the channel, and you have more heat losses, less heat reaction, eventually flames stop to propagate into it. That critical diameter we call quenching diameter, right? So this quenching diameter, if we rewrite this equation, it defines the H. The H will be defined by Newton number, which is heat loss, and the flame thickness. And so the heat loss is proportional to the square of the channel diameter, and then activation energy. So the quenching happens as this term becomes the inverse of E. This defines the quenching diameter. The quenching diameter is proportional to the E, activation energy, Newton number, and flame thickness. So this again is governed by the activation energy, and then that the heat losses. If you have a plasma, you can change it. This is all because of theory. And then how does the plasma really affect extinction? A few years ago, and we did this kind of a diffusion flame extinction. You measure the extinction of all fuels, jet fuels, from alkanes, aromatics, isoalkanes. If we plot the extinction limit as a function of fuel mole fractions, they differ each other because they are the aromatics, isoalkanes, and alkanes, they have different reactivity. Right? Alkanes more faster than aromatics. So therefore, they have a higher extinction limit. But if you normalize all this extinction limit by using the radical production or radical index, and then the transport weighted enthalpy, and I mean how much the heat you generated due to the diffusion transport, you can see that all these things, they fall into one line. That one line tells you the reactivity, the radical index of different fuel. So you can use in this curve to rank all the reactivity of different fuel. And plasma can do. The plasma can change the reactivities and also change the transport properties and extend your extinction limit. And here is that does plasma really enhance the flame speed? That is the question that we were asking. That we can do that the extinction of diffusion flame. We put a gliding arc in the bottom. We see that how does plasma really enhance the flame extinction limits? And my rate analysis tell me that plasma cannot do much things in affecting the extinction because the chain branching reaction is much faster than the plasma process. So I'll just show you the experiment. This is the experiment that basically shows you the extinction strain rate as a function of a different methane concentration. This is that without plasma. This is with plasma. You can see that the extinction limit is enhanced by more than factor of 2. We thought this is a great indication of plasma enhancement of extinction limit. But is this kinetic effect or this is a thermal effect? Then we did another experiment by raising that same temperature and using this energy consumed. We've compared the radical production by OH using laser-induced fluorescence and the temperature measured by Rayleigh scattering. We found that the entirely the same. You're using plasma or using heat to the same temperature, you got the same extinction limit and strength structure. That means that a non-equilibrium plasma by gliding arc, they only have thermal effect. They don't have much of kinetic effect, enhance your flame speed because the temperature is high. So that was the conclusion we made. But plasma can generate a lot of species, for example. They can generate NOx and ozone, which is quite stable. They can also generate a singlet oxygen, which is quite stable too. They generate a minutes of stability. You can generate all different radicals. And the question is, how does the plasma really, ozone and this singlet oxygen, can they really enhance ignition? Remember, so this is at the lifted flame we did. We tried to generate a lifted flame of propane. We tried to put a lot of ozone generation like plasma. If ozone can enhance the combustion, this should be increase my flame, leading the flame speed of a partially primitive flame, so that my lift height will be decreasing with the increase of reactivity. So what that did is that this is at the probably the flame speed. This is at the enhancement. We put probably a 500 ppm or to a 1,000 ppm ozone. The maximum enhancement we saw is only 8%. Generating 1,000 ppm of ozone is not easy. You have to generate a lot of enthalpy change. But you only have 8% of enhancement of flame speed. That means that again, the kinetic effect by ozone generation in terms of a flame speed enhancement is not a first of order magnitude to consider. And this is that the major reaction is that the ozone basically, before the flame front, they dissociate into atomic oxygen, and that attacks the fuel, generate radicals. Again, this process is slower compared to the chain branching by itself. They can enhance that the flames, but not much. They have this is that the thermal effect. If you dissociate into this by adding energy, this is the kinetic effect due to the ozone. They have some kinetic effect, but the kinetic effect is not really large, a few percent. That compared to that ignition is order of magnitude, right? And this is another one is that the combustion process is governed by H plus O2 branching reaction. This reaction has high activation energy. It's quite slow unless you go to above 1200 Kelvin. But if your plasma can generate O2 singlet delta, this reaction is the same reaction, but it's 100 times faster. So if you can generate 1% of oxygen into O2 singlet, you can double the flame speed, chain branching ratio. So if you look at the energy diagram, and this is the oxygen ground state, the O2 singlet is here, only need about 1 electron volt to generate it. Very low energy cost. So therefore, the O2, A singlet, a B sigma, you only need a 1 electron volt and to excite it from ground state to this. And then we can change the chain branching reactions if we can selectively generate O2 singlet delta. So at that time, I didn't know how to generate O2 singlet delta. It's very difficult to generate. In the end, we had the electron energy has to be very low. Otherwise, you can't generate. So therefore, we tried using a microwave DBD discharge to make that electron energy lower so that we can generate O2 A singlet. Here is the experimental result that we produce this O2 A singlet. We're using ICOS cavity. It's just like that cavity went down to measure that O2 A singlet. And when you produce O2 A singlet, you also produce ozone. We use NOx because NOx reaction with ozone is very fast. This is the ozone depletion effect in the atmosphere. So we introduce some NOx to remove this ozone so that we can observe that the O2 singlet effect to see how much they can enhance flame speed due to the new reaction pathway for chain branching reactions. Here is the result. The result is very, this is that laser absorption, ICOS, to measure the O2 singlet. And this is that the ozone laser absorption to measure the ozone concentration. This measurement, and then we can see that by producing 5,000 ppm of O2 singlet, and my flame speed is only increased by a few percent. And this is rather discouraging. Mostly that we expect that this will dramatically enhance flame speed, but did not. Mostly the O2 singlet is generated when you mix them with the fuel. They collide, they're quenched. So plasma, in principle, that they can dramatically enhance the flame speed due to electronically excited oxygen, but practically, it is quenched by many other things, and you cannot observe that the new reaction pathway to enhance the flame speed. So this is one of the reactions. Conclusion we learn. So the next thing that the atomic oxygen production. So let's using a non-equilibrium plasma to break down the oxygen into atomic oxygen, because atomic oxygen is so reactive, is radical. So let's see how that react to extinction limit. So here you can see this is that the pulses is probably 7 kilovolt. Is that probably 50? The pulse width is about 15 nanoseconds, and we have a counterflow flame, and we generate this is the electrode. This electrode, they serve as a nozzle and also serve as the electrode. So we can generate that atomic oxygen and see how that affects the extinction limits. If that does not affect any extinction limit, we probably have to give up. What plasma really can enhance the flames. So this is the measurement of atomic oxygen production by Talif, and we measured and using different plasma repetition rate, and it does increase with that plasma repetition rate. This is the extinction limit, and enhanced by that a nanosecond plasma, and no plasma, and with plasma. What you can see that if you compare those things, you do see the enhancement of extinction limit by producing atomic oxygen. But if you really consider how much is the thermal effect, how much that is the kinetic effect is like this, is a decimal. So in combustion research, always I tell my students, don't do research which is addressing something in a decimal. Okay? You want doing something in the research is really addressing something in order of magnitude that drawing new science or new physics. So I was very disappointed at this, and at the time I said, let's don't do any kind of a plasma-assisted flame speed anymore, because from theory and from experiment, we don't see much of this effect. Rather, to do something at a low temperature, intermediate temperature, there plasma can win, right? So that totally changed from my philosophy from 2010 experiment. So now that I try to show you something that plasma-assisted cool flame. This got me to this field. So I say I cannot win for high temperature flames, but maybe I can win for low temperature flames, because the reactivity of plasma is much higher than the low temperature reactivity. So you have two-stage ignition, and here is a diagram I'm going to show you that when you consider cool flame. This is flame temperature, this is equivalent ratio. This is high temperature flame. Below 1200 Kelvin, everything dies. But if you consider a cool flame, and you have a new flame branch, which has a lower temperature, and it's about 700 Kelvin, they can burn much leaner. They can also burn much richer. That is at the lower temperature. So the existence of a cool flame dramatically changed the concept of flammable limits by high temperature flame, and dramatically changed the numbers of burning limit. But the most interesting that the plasma can dramatically enhance this, because the reactivity of cool flames is much slower compared to the plasma process. So this is that in the laboratory we developed this kind of a plasma-assisted cool flame formation, a plasma-assisted, a mostly ozone-assisted a cool flame compared to the flame. And this experiment basically showing that the plasma can dramatically extend the burning limit of the cool flames. And then what I try to see that from here, the plasma is really that is a complicated process. You got thermal effect, kinetic effect, and transport effect. But that the kinetic effect, that really the plasma can win is the lower temperature. As the lower the temperature you go, and the better the plasma properties will be, particularly for reforming, for low temperature ignition, for low cool flames. So this is open an entire new area for combustion control at a lower temperature. So the next thing to try to answer is that plasma not only generate radicals, but also break down the large field to small ones. They change your Lewis number, right? What is the Lewis number? The ratio of mass diffusivity by the thermal diffusivity. How does the Lewis number affect the flammable limits? Do you know? Anybody know? Does what? Doesn't. Okay, doesn't. So I thought it didn't, but I will show you. So let's say that this is at the a stagnation plane. This kind of flame. I just love kind of flame because that is so simple, allow you to do a lot of things in theory. So you can write down these two equations: energy by introducing that a Lewis number effect, rho d, and introducing a heat losses. And then you can using this system, you can study what is the flammability limit affected by Lewis number and heat loss. And then I don't go to the details. There's too much details. You can look at the thing. I try to show you the result. This is the jump conditions. So here is the result. The result is basically showing you that the 8F is the location of the flame from the stagnation plane. Okay? The A is the strain rate. And the G is some kind of function you don't. The E exponential function about PF. What is PF? PF is the Lewis number effect. L is the reduced limit, Lewis number minus 1. Okay? And this is that the H plus is the heat loss after the flame due to radiation or due to what heat losses. H minus is that the heat loss in front of the flame. So if 8F equal to infinity, that means my flame standing infinitely from the stagnation plane. What is that? It's a planar flame, right? With zero strain rate, correct? So that equation goes to this. This is that the equation I showed you before. A planar flame defines the flammable limits of planar flame. This equation defines the flammable limits of stretched flames. Okay? How does the stretched flame behave differently in terms of burning limit from the planar flame? Anybody know? Okay, here is that I show you some numerical result I showed you. This I did it probably more than 15 years ago. If you have a Lewis number less than 1, and this is that strain rate, this is at the flame location from the stagnation plane. So you can see that this is the flame location. At high strain rate, you have stretch extinction, the flame will die. At the lower strain rate, you have radiation extinction, the flame will die. The flame can only survive between a range of strain rate in a stretched flame system. Okay? When you slightly increase that the fuel concentration, you can see that I have a small area, flame can stabilize between this system, broader area. Then I have another flame standing far away from the stagnant plane. I have two solutions at one condition. As you further increase the fuel concentration, and this far standing flame move towards the stagnation and eventually recombine, form this entire flame diagram. What does it mean? Well, it is very difficult to understand what does it mean. And now I show you one paragraph. This is the experiment we did in the microgravity as a countable flame. This is at strain rate. This is at the equivalence ratio. This is at the one-dimensional planar flame's flammable limits. Okay? This is a methane air stretched flammable limits. You can see the stretched flame is burning thinner than the planar flame because there's the Lewis number effect. Okay? So for propane, the Lewis number is larger than 1, and you can see the flame, the stretched flame, linearly extrapolate to the unstretched flame. For Lewis number less than 1, and you don't. So therefore, the burning limit of stretched flame is highly governed by the Lewis number. And one large Lewis number you can linearly extrapolate, and the lower Lewis number you can't, because that the strain rate help that the combustion when the Lewis number less than 1. So what is that the burning limit? If you plot it, so here is my flame temperature, here is that strain rate. If Lewis number is less than 1 is above 1, at very lean conditions, equivalence ratio 0.45 for methane, nitrogen, helium, you have a flames only stable in a certain range. As the equivalence ratio increase, this flammable region increase. And on the other hand, you have another flame here and expanding, and eventually the two things merge. This is how that even for Lewis number larger than 1, you still have, even for Lewis number larger than 1, the flame still burn at the linear conditions with stretch, and then the unstretched flame. Why? So if we plot a 3 dimension, plot that this flame temperature as a function of stretch, this is the equivalence ratio. On this flame temperature equivalence ratio plane, this is the flammable limit, lean and rich limit. You learn from the textbook in combustion. Irv Glossman, Professor Law, they show you this one, project on this one. This is that the curve, 3-dimensional curve I created. You can see that you see this is that a new island that burn much linear than the planar flame if the Lewis number less than critical value. If you project this 3-dimensional diagram onto the plane of equivalence ratio and strain rate, which I just showed you before, this is that the flammable limit of planar flame. This is the flammable limit of stretched flame. You can see that the stretched flame has a linear flammable limit than the unstretched flame. So this is, I call this a G diagram. So basically saying that this is that the stretch extinction, this is the equivalence ratio. This is the planar flame extinction limit. This is that the stretched flame. So for hydrogen, because the Lewis number is much less, you can see this is the planar flame burning limit. This is a stretched burning limit. It's much linear than the planar flame. So change that the Lewis number, reduce the Lewis number, can dramatically enhance the lean burn limit if plasma can do that. The plasma can break down the large field to small ones. They can extend that extend our lean limit to this kind of a lean burn limit as well. And for large alkanes, you can dramatically extend it. There's no magic for that. So now we try to understand, and what is that 10 more minutes, the plasma effect on minimum ignition energy. So first of all, what is that the minimum ignition energy? For example, if you have a gas turbine engine, do you still have time?